All right, good evening, everyone. My name is Alnisha Simmons, and I am a senior biology lecturer here at Bermuda College. On behalf of Bermuda College, it is my pleasure to welcome you to tonight's public forum. We are delighted to have you join us for what promises to be an engaging and insightful discussion featuring our guest ROCHE speaker, Dr. Mark Guichard. We would like to extend special thanks to Bermuda College President Dr. David Sam for his continued leadership and support, as well as to our ROCHE corporate sponsors for their partnership and commitment to advancing scientific dialogue in the community. We also recognize and appreciate the dedicated members of our science team whose efforts made this event possible. Can I have those members of the science teams to stand? We have Dr. and I just like to introduce them. We have Dr. Renier Jeffrey, who is our chemistry lecturer. We have Dr. Andrew Danu, biology, Miss Amy Harvey, environmental science, Miss Leanne Hinton, who is our laboratory supervisor, and hiding over there is Miss May Wee, who is our laboratory technician. And we also have, did I see, Paul, why aren't you standing up? Paul is our adjunct physics lecturer. Thank you. At this time, it is my honor to invite Dr. David Sam to the podium to officially welcome you as well as our honored speaker, Dr. Mark Guichard. Thank you.
Good evening. Oh, no. Oh, no. Good evening. Welcome to Bermuda College. On behalf of the Board of Governors, faculty, staff, students, welcome. This is a topic that people should be listening to every day because the subject matter impacts us on a daily basis. And I'm glad that you are here this evening to get a first-hand knowledge of this very important topic. And Mr. Speaker, I've decided that I'm going to have some tough questions for you. And so, this hurricane season be hazardous? Will climate change continue to have impact on the island? Will it remain risky? And will the people of Bermuda continue to be resilient? Well, this is the place to get answers to such questions. And I'm excited that you are here this evening to listen to this important topic. At this time, I will invite the ROCHE scholar, Julio Rivera Cabrera, to come up and introduce our distinguished speaker.
Good evening, everyone. Dr. Mark Guichard is the Chief Operating Officer of the ASU Bermuda Institute of Ocean Sciences and a professor of practice in the School of Ocean Futures. He is a chartered meteorologist with over 25 years of experience with atmospheric sciences. His research into Atlantic hurricanes and subtropical storms led him to obtain a PhD in meteorology from Penn State University, following a master's degree from the University of East Anglia. Mark has experience as an operational forecaster with training from the UK Met Office and the US National Hurricane Center. Mark was the director of Bermuda Weather Service from 2006 to 2012, as well as 2020 to 2023. He has served on intergovernmental committees focusing on warning and mitigation of natural hazards, and has also worked as a reinsurance analyst and catastrophe risk modeler. He has been a regional focal point for disaster risk reduction for the UN World Meteorological Organization. Mark, our Bermudian, has a long history with BIOS, having been a Bermuda program intern in the mid 1900s and a previous adjunct faculty member. More recently, he was the program manager of the Risk Prediction Initiative at BIOS from 2013 to 2020, with responsibilities for supervision of all RPI activities. Mark was also the director of corporate and community relations, overseeing local stakeholder engagements with BIOS. Mark's current research and education interests include variability of Atlantic hurricane risk, Bermuda's weather and climate, and disaster risk reduction. So it will be my great honor to introduce you guys to Dr. Mark Guichard.
Well, thanks very much. I think you've just given half of my talk. So I'll see you all later. No. So good evening. Thank you very much for having me here. I'm very honored to be a speaker here. Thank you to the sponsors. Thank you to Bermuda College for inviting me. I'm very honored to be here amongst Bermudian scientists. My talk today is going to be about natural hazards and climate change, and also risk and resilience in small islands specifically, like Bermuda. But before I start, I wanted to acknowledge and dedicate this talk to the memory of my late Uncle Bertram Guichard, who was formerly the Dean of Arts and Sciences here at the Bermuda College. And he began here in 1963 when it was the Bermuda Technical Institute. So he oversaw and was part of the change over to the Bermuda College. So again, very honored to be standing here today. In terms of my talk, again, you just heard half of it, but how did I get here? Some of my experiences in science in Bermuda, how that translates into management and even into sort of policy advising, looking at moving towards more pure research, Bermuda Institute of Ocean Sciences and what we do there, monitoring the ocean and the atmosphere. I will take a portion of this talk and focus a bit on collaborations with students and mentoring students, Bermudian and international students, and also then wrap up with talking about some of the latest research I and some of my colleagues have been doing. So first of all, first steps in environmental science in Bermuda were taken back in the late 1900s. You heard it earlier. The 1980s, I was a student at Work Academy, and we went on a field trip to Walsingham Jungle here. And Walsingham Jungle, otherwise known as Tom Moore's Jungle as well, is a fascinating spot here in Bermuda that has all sorts of geological, ecological, and aquatic features associated with it. Just here in this photograph of this sinkhole, you have stalactites and stalagmites from the old cave. The sinkhole has filled with seawater, and you've got sea life within that sinkhole. You've got mangroves off to the side. You've got all the different strata of the rocks, so fascination to geologists, ecologists, and anyone interested in the natural history of Bermuda. You can see it all in this type of image and by walking through this type of environment here in Bermuda. So one of the things I did when I was an intern and a student back in the 90s was one of my first studies that I did was going to environments such as this and examining the water quality, examining the chemical constituents of the water and the trace chemicals, and coming up with graphics like this. This is before Excel, et cetera. But what we would do is we would take an instrument or a piece of equipment that we use even to this day, called a Niskin bottle. And this is a Niskin bottle. So what I would do is, looking in a more untouched environment cave, such as some of the ones that you can find in Walsingham Jungle, and also look at the more commercialized caves like Crystal Caves and Leamington Caves at the time. And I would take this bottle, which is commonly used in aquatic and oceanographic sciences. And what this bottle does is it opens at both ends, and I'll put the mic down. Hopefully you can hear me at the back. What it does is it opens at both ends, and it has a triggering mechanism. It has a triggering mechanism that enables both ends to close. So what you do is you lower this down on a rope, you send a messenger weight down that triggers it, and it closes on both sides, captures water at that depth, and then you can bring that water up to the surface and sample it from this spigot here. And so you can imagine me carrying this down into the depths of crystal caves. Anyone been to crystal caves before? How many steps are there? A lot. That's not so bad. It's carrying it up full of water. That was the problem. But in any event, you do these types of things in the name of science. So I'll come back to the Niskin bottle a little bit later, but that was sort of one of my first research projects. And from that point onwards, I was hooked. I spent some time at BIOS, as it was known back then, the Bermuda Biological Station for Research, BBSR. In the 90s, I worked under Dr. Kent Simmons, who is another Bermudian scientist, and my mentor at the time in the air quality and environmental quality lab that was focusing on sort of air quality, water quality. And this was around the time that Tynes Bay incinerator was being finished off and coming into being commissioned. And so it was very important to capture the quality of the air around that site. We did a lot of things like measuring tank water quality as well. And so all of that type of thing, measuring pollution and atmospheric and aquatic contaminants was part of what I was really interested in. And that led me to get an environmental sciences degree at the University of East Anglia. And I was very interested in this air pollution, atmospheric chemistry piece. So I went on and did a master's in atmospheric sciences. Now, when I finished that master's, I came home to Bermuda, and my experience of meteorology, having done that master's degree, was very much equations. I hadn't seen practical applications of meteorology and climate science yet. And so my focus when I came back home was very much this pollution piece. And I did a bit of work at Belco for their environmental office as an intern as well. But in the mid-90s, there was an event that happened that sort of changed how we operate here in Bermuda, and that was that the US Navy left. And up until 1995, the US military had operated all of the airport functions, all of the airport operations and support functions, including meteorology. So there's air traffic control, there was ground electronics, and then there was the Bermuda Weather Service that was operated by the U.S. Navy up until 1995. And so when I came home in 97, I think it was just the right time to be in the right place. They were hiring Bermudians. I came to them with a master's in atmospheric sciences. So I thought at the time, this could be interesting because this isn't just equations. This is, I see, oh, we get to play with toys. Like we have radar, there's weather balloons, there's satellite, there's all sorts of interesting computer models that we'd be working with. This isn't just equations on a chalkboard. And also, it actually paid real money. So that was an important thing coming straight out of graduate school. During my time in the Bermuda Weather Service, I forecasted a number of different tropical storms and hurricanes. I worked with lots of Bermudian meteorologists. I could name almost all of them. I won't embarrass them here, but I was able to really get a sense of this growing community within the atmospheric sciences here in Bermuda that didn't exist before. So my first hurricane forecast was for Hurricane Gert in 1999. That was the one where there was a big storm surge and the dolphins at Sonesta Beach got escaped. That was my first memory of forecasting hurricanes. One of the storms that impacted us here in Bermuda was Hurricane Karen, and it was deemed to have come out of nowhere. It was, you can see in the bottom left here, this is a satellite image of subtropical storm Karen as it was. And you can see it has this very asymmetric shape. It doesn't really look like a hurricane, and yet it produced hurricane force winds and gusts. And the pressure, the barometric pressure at the surface drops down to the types of pressure you would expect in a hurricane. And all of a sudden, the power across the island was out. And less than 24 hours later, it looked a lot more like a classical tropical hurricane. To be fair, we got a lot of flack for that at the Bermuda Weather Service. Surprise storm hits the island, Weather Service sort of on the back foot. There was enough warning. I wasn't forecasting that day, so you can't blame me for that one. But it was of great interest to me that something so unlike a hurricane to start off with could actually cause so much hurricane-like impact here on the island. And this kind of led to my growing interest in actually doing research, actually studying some of the things that I've been forecasting operationally for so long. So I was able to secure a position to go and work as a graduate student at Penn State University, where I got my PhD. And I had an opportunity to go and study back in the UK at the University of Reading, or at the University of Miami. And these are places that I kind of wanted to go to, but know myself well enough that I would get very distracted. And also, I knew that I had a mission, and my mission was to study this particular phenomenon, not whatever my PhD advisor decides. And so I went to work with Jenny Evans, my former, my now late former PhD advisor, who was in fact studying these systems. And fast forward 4 years later, I was very fortunate to have my first publication in Meteorology and Atmospheric Physics, a journal, a scientific journal, alongside some of my colleagues at the Bermuda Weather Service. So it wasn't just me benefiting from doing some of this research. We were able to sort of operationalize some of the work that I was able to study. And with Liz Nelson and Declan O'Connell, now Liz Harris, and others, we published this paper. So I finished up that PhD in 2006, and as the sort of, I guess, top qualified Bermudian meteorologist at the time, I'd done some forecasting work. I worked in the operation. I now have my quote unquote hunting license to go do research. So I had these qualifications, and my boss was retiring, and they said, would you be interested in sort of looking at becoming a manager, becoming the head of the Weather Service? And I said, yes, that's definitely something I'd be interested in. And so I was thrown from, I had to pivot suddenly from being a scientist and an operational communicator to a supervisor and a leader and a spokesperson for the Bermuda Weather Service. And so here's a summary of what I learned that first year. You ready? It's easy. It's like riding a bike, except the bike's on fire and you're on fire and everything's on fire. Thankfully, I was able to get some management training. And that holds true today, of course. I've been a manager ever since, and there's no end to the firefighting. So despite the fact that I had to transition to management and I had this really steep learning curve, I found the training that I'd received as a graduate student doing science and as a forecaster was invaluable practice. That grad student piece meant that I now had experience juggling many different priorities. I knew how to project manage and sort of manage different priorities like classes, exams, independent work for the PhD. And that led to some great opportunities, not only within the science, but also within the operation, and to interact with international colleagues across the field. That led into working with groups such as the World Meteorological Organization, the Hurricane Committee. At the far right there, you can see me and the other first Bermudian meteorologist, Kimberly Zuhl, who was the deputy director of the Weather Service at the time, hosting the Hurricane Committee here in Bermuda in 2010. And there I am advising the EMO and the country in advance of hurricane impacts. So I got a lot of experience, not only understanding and trying to understand more about the science of hurricanes and tropical storms and subtropical storms, I also had a great opportunity to become more advanced in communications and have an opportunity to share what I knew with the public, much like I'm doing right now. One of the interesting aspects of doing these intergovernmental sort of coordination groups is you get sort of, if you're an expert in one thing, you often get lumped in with other experts in other fields. And on small islands, we have a very small cohort of expertise, and so often we have to multitask. In 2004, many of you may remember this, there was a, on Boxing Day, there was a massive event. There was a tsunami that was spawned in the Indian Ocean off of Indonesia, and it impacted hundreds of thousands of people, well, millions of people. It killed hundreds of thousands of people, unfortunately. And it became very apparent that meteorological services, such as the Bermuda Weather Service, had to certainly step into this role of issuing warnings for phenomena that we hadn't really studied specifically. So there was this event, and what you're looking at here is a plot of the amplitude, or the height, if you will, of the waves, the tsunami waves, from the point of origin, the undersea earthquake off Banda Aceh in Indonesia, that's that red star there, and how that energy propagated outwards. The white lines represent an hour from each hour from the onset of the earthquake. And you can see that the tsunami waves themselves didn't just impact the Indian Ocean, but went all over the world. And by the time they got to us, we didn't see much of an impact at all. But to be sure, the tide gauge did measure a small tsunami. So, we started to have to really think about, well, what happens operationally if we have one of these events in the Atlantic? So subsequently, after 2006, when there was a false alarm here in Bermuda, Bermuda Weather Service became the focal point for tsunami warnings. And so a lot of the time that I spent doing work as a researcher in the environmental sciences was now having to be applied to understanding this other oceanographic phenomena that I didn't really have that expertise in, but I did have expertise in understanding science, communicating science, and issuing warnings. And so it made sense that the Bermuda Weather Service did become the focal point for this, this type of event. I'm going to take a small sidebar. It's going to become apparent why in a minute, but we're going to delve into some of Bermuda's past, Bermuda's history. And in particular, King's pilot James "Jemmy" Darrell in the 17 and 1800s. Now, when I was in the Sea Cadets in St. George's for about 30 years, from when I was a cadet to when I finished up as one of the officers, through that organization, I learned a lot about this individual. He was an enslaved pilot in St. George's, known for his skills on the sea. There's the sort of fairly well-known history about him that he was one of the first Bermudian landowners. He was given his freedoms. He was set free after having piloted a massive Royal Navy ship of the line, HMS Resolution, into what became known as Murray's Anchorage, named after the admiral of the fleet at the time. And so he was highly regarded as a very skilled pilot and sort of navigator around Bermuda's waters. One perhaps slightly lesser known fact about him was that he and two other enslaved pilots, amongst others, contributed in a large way to mapping the platform. In the late 1700s, I'm going to say 1780s and 90s, there was an effort by the Royal Navy to map the seafloor topography, otherwise known as bathymetry, of the island and its platform and its reefs. And the way that they did that, I'm going to pull out another prop here, is by using a lead line. And this is my poor man's attempt at a lead line. It's basically a weight on the end of the line. So you imagine 3 or 4 men in a boat. Let's go down to where this hits the seafloor. Okay, all right, 1, 2, 3, that's 3 fathoms. Now imagine doing that tens of thousands of times over the course of a decade. And that's what they did. And they came up with this map. It's the first known, or the first well-regarded, I should say, bathymetric map of Bermuda. So you might say that's all great, but how does it hold up today? Well, let's look at a recent NASA satellite image. Looks pretty good to me. And we'll just do that again so you can get a view of the reefs, where they are, where the shoals are. So you can see 200 years plus later, the legacy of this work that has been done by those that didn't necessarily receive recognition for it. I think of Jemmy Darrow and his compatriots as one of the first, well, the first Bermudian oceanographic technician. So I hope that link there became apparent. We're actually, to this day, to my knowledge, organizations like NOAA have incorporated this original data into the models that they use for storm surges and for tsunami modeling and for wave modeling that they do at the Bermuda Weather Service. So again, that's quite impressive that centuries later, this gentleman and his friends made such a lasting impression on some of the science that we do today. So let's go back to BIOS, the Bermuda Institute of Ocean Sciences. I'm going to tell you a little bit about some of the things that we do there. After about 15 years at the Weather Service in various roles, culminating as its director, I took a brief detour into the reinsurance market. I decided, time to do something else while I'm still young enough to do something else. And I worked as a catastrophe risk modeler at one of the reinsurers in town. That lasted 5 months. And the reason it lasted 5 months was because this role came up at BIOS, a lot more in tune with my desire to do more pure research. While I was managing this program, I was still liaising with the insurance industry, but I was also connecting them with academics like myself, doing work with some of my fellow meteorologists, but we were also studying earthquakes and tsunamis, tornadoes, winter storms, all the things that cause damage and chaos, to get a better handle, a better understanding of what those natural hazards have in store, especially in a changing climate. But it's sort of, if you don't know much about BIOS, you might ask the question, well, like, why BIOS? What does BIOS even do? So the Bermuda Institute of Ocean Sciences is an American institution. It's based here in Bermuda by virtue of easy access to the deep ocean. An American institution of oceanography based on the east coast of the United States might have a research vessel that takes 2 days to get to deep water. And when I say deep, I mean over 2 kilometers deep. Whereas we can get to 4 kilometers deep in about 2 hours, just off St. George's. So BIOS has been around in various incarnations since 1903. And for the last 70 years, it has developed the longest running time series of deep water observations from anywhere in the world. So it's kind of like a snapshot of what's going on in the Atlantic, and it's based right here in Bermuda at Ferry Reach. In addition to the oceanographic observations, there is an atmospheric observatory as well at Tudor Hill in Southampton, just off Port Royal. And so it's also measuring atmospheric constituents in the marine atmosphere. Our research vessel there, the Atlantic Explorer, which you can see the photograph of in the right, goes out to these same spots in the oceans, Hydrostation S, about 25 kilometers southeast of the island, and the Bermuda Atlantic Time Series study site, about 80 kilometers southeast of the island. We like our acronym, so that's called BATS. And it's been doing that again since the 1950s. In more recent years, that BATS deployment area has been the focal point of a lot of our attention and international researchers as well. And what has it shown us? Well, I'm going to show you a series of graphs here to really get at like what are some of the key outputs of this data set that we've been developing for decades. One is that the surface of the ocean has been warming over the last several decades. Since the 1950s, it's warmed up about 1.5 degrees. Now you hear about the Paris Accords and the notion that we should not, the global surface air temperature should not be allowed to exceed 1.5 degrees Celsius, or else there's a lot of larger impacts that we might face. But that time frame is based on the starting point of the Industrial Revolution back in the 1800s. This is just in the last 70 years. So the surface of the ocean is already absorbing a lot more heat than the atmosphere. Sorry, it's absorbing a lot of heat out of the atmosphere, which means that it's warming up. And another perspective on that is the duration of summertime temperatures in the ocean is getting longer. What's that doing to salinity? Well, as the surface of the ocean gets warmer, there's more evaporation, so the near surface layers get saltier over time. So there's a salinization, if you will, of the upper ocean that's continuing on and on and on as we get more warming. It's also becoming less oxygenated. That means oxygen in the near surface waters is decreasing over time. This all kind of goes hand in hand with what we're seeing in the atmosphere. We have increasing carbon dioxide. This is in line with what we see from around the world. You can see some seasonal variation there year to year, where you have sort of troughs and peaks in the amount of carbon dioxide in the atmosphere as respiration and then photosynthesis take over or dominate the process. But you can see the trend is most definitely upwards. And that lines up very nicely with what is seen in, say, Hawaii, where there's a much longer time series. Some of that CO2, that carbon dioxide, is being taken up by the surface ocean. And so we're also measuring a rise in the amount of carbon dioxide in the surface ocean. And that means that the surface ocean is becoming more acidic over time as well. So we're measuring all these trends, and you wouldn't necessarily know about them unless you made the effort to methodically go in year after year, month after month, and actually take these measurements. The value of these data is immeasurable. They go into climate models, they go into other fundamental research about how the oceans are behaving, and they're also able to tease out interannual variations as well. So it's not just about those long-term trends, but the long-term trends themselves are, in fact, are quite shocking. So the oceans have absorbed about 90% of the excess heating produced by these additional greenhouse gas emissions that humans have produced. And the temperature of the upper ocean in Bermuda has been rising slowly over the decades. And there's been pretty robust evidence by the BATS time series, the Bermuda Atlantic time series, about this. So I've kind of already shown you this long-term trend. This one goes back to the 80s. This is the BATS site. That's 80 kilometers southeast of Bermuda. Another perspective on this gradual warming is that in the same way that you have heat waves in the atmosphere, in fact, there's a big heat wave going on right now in the western part of North America. I believe in Phoenix, some of our colleagues at Arizona State are suffering temperatures of 108 degrees Fahrenheit today. So when we complained in our health and safety meeting that today that I was chairing, that when it gets a bit warm, we need to up our air conditioning. There was some reason we were talking about it. They just started laughing at us. In any event, you get atmospheric heat waves. You also get marine heat waves. The duration and intensity of which are increasing near Bermuda. This is a plot of those heat waves near Bermuda. And in another perspective about all of this, we look at this duration of what I like to think of as summertime temperatures. How many people grew up not going in the water to go swimming before May 24th? Because before then, it's just like, ugh. Now, the duration of these warm temperatures, 28 Celsius or 82 Fahrenheit, is much longer. You can go in at that time and expect to be swimming all the way through the summer to the end of, say, September. Whereas before, you had a very short window where you had those types of temperatures. So from the ocean's perspective, summertime is getting longer here in Bermuda. But this is all really interesting, but so what? I think the so what is we are seeing hazards that are resulting from these changes over time. Some of them are more obvious than others. As the global average surface temperature warms, glaciers melt, land ice melts, and also the absorption of heat by the oceans leads to its expansion. Anyone in the physics class will tell you that you heat something up and it expands. You heat up the oceans, they expand. And so those two effects combined mean that we have sea level rise globally. Regionally, it will be different in some places than others at different rates, but we do see sea level rise, and I'll talk a little bit about that later. We see stresses to our ecology in the marine environment. Those marine heat waves, those periods of extreme temperatures for corals means that the symbiosis that those organisms have between the zooxanthellae, which is the algae that gives it its pigment, and the coral polyp, the animal. I'm gonna check later to see if I got that right, Alex. That relationship gets stressed, and so the coral expels its zooxanthellae. The coral goes white. It's called coral bleaching. You may have heard of it. So when corals get stressed by, amongst other things, heat, they can bleach. If they have an extended bleaching period, they can die. And when you get dead corals, you just have these skeletons of corals around. We, fortunately, here this far north, have not seen mass bleaching events that have caused lots of coral death, but to be sure, this is something that bears watching. That and other impacts to the marine environment can lead to effects on our food webs, not only in the nearshore and coral reef environment, but also in the deep. Back to the meteorology side, we get heavier rainfall events. As the surface of the Earth warms, the air as it warms every 1 degree Celsius, theory tells us it should be able to hold about 7% more water vapor, and that gives more moisture to be available for extreme rainfall events. And how many times have you turned on the news and seen this place is flooded and that place is flooded? If I say the words to you, Bakery Lane, what does that mean to you? The type of flooding we get here is nuisance compared to some of the major impacts that some countries have. But to be sure, we are seeing more intense, heavy rainfall events. And the thing that I study, hurricanes. We're seeing more hurricanes. We're seeing more intense hurricanes as well. And we'll get into a little bit about what that means for us shortly. So while I was at the Risk Prediction Initiative in BIOS, I was taking some of these findings and translating what I had learned from sort of local oceanic and atmospheric observations through the lens of natural hazards. And I was able to explore a little bit more of the societal impacts of these large-scale changes. And so we were able to engage with local partners to participate in, and even in some cases lead some of these key events that have kind of led Bermuda's focus on climate change, from the reinsurance industry, the Climate Risk Forum that we did with the Tourism Authority back in 2019, the Youth Climate Summit, which was led by the Bermuda Underwater Exploration Institute, but we certainly have played a role in that as well. So a lot of key events, and also we've been involved with collaborations on island and with global scientists and risk analysts, leading to publications with local and international relevance. Here are three. This was a short report that we did following Hurricane Faye and Gonzalo. Remember those events back to back within 1 week of another. Faye came through and everyone kind of went, what was that? Okay, back to normal. And then the main event came through, Gonzalo, which was a Category 3. And it turns out that Hurricane Faye cooled the surface of the ocean enough to weaken Hurricane Gonzalo before it came through. And so although Gonzalo was impactful, it wasn't nearly as impactful as it could have been had Faye not come through. So this interplay between ocean temperature and hurricane intensity, that fascinated me. So I wanted to do a little bit more work on that. Some of the ways I've been able to do that type of work is with students. And we have a number of different activities at BIOS. These are students that I think these are pretty much all students I've worked with over the last 15 years or so, doing computer modeling, launching weather balloons, going out to sea. We have students from Bermuda, UK, China, Panama, Cyprus, all working with us at BIOS on these hurricane problems. Teaching classes on modern observational oceanography, going out on the ship, lots of opportunities for students. And a lot of these collaborations led to short reports, in some cases peer-reviewed publications. And in 2022 and 3, I decided it was time that we needed to compile these all into one place so that we get a synthesis of what are the effects of climate change on Bermuda based on the last 10 to 20 years worth of research that we've been doing, not only at BIOS, but in other places as well. And so we compiled these reports, Climate Change in Bermuda, following the IPCC sort of format. Part 1 was about the physical science and the actual hazards themselves, the piece that we like study, meteorologists, oceanographers. And then part 2 was more focused on what are the impacts to society here in Bermuda. In some cases, a little bit more difficult to get your arms around. It's one thing to say the temperature will be this. It's another to say, well, what does that mean for people? And so a lot of that work is synthesized in these reports. Some key findings in those reports. Well, I mean, again, the physical hazards. One is more frequent and stronger hurricanes. And if you were to ask me 20 years ago, are we likely to get a Category 4 storm here in Bermuda? I would have said, it's not very likely. It could happen. If you ask me today, I'd say just yes, absolutely. We have had many near misses already from Category 4 storms, so it's only a matter of time. Heavy downpours, and I mentioned Bakery Lane. There's 2 men in a boat in Bakery Lane, resulting from these heavy downpours that seem to be happening more frequently. Now, to be sure, there are other reasons why certain areas flood. There's poor drainage, the fact that it's sort of at or below sea level, there's a canal going by, all of those things, but the trigger is heavy rainfall. So one of the pieces of work that we did was with another Bermudian meteorologist, Dr. Michael Johnston, who was able to publish some work on the frequency of heavy rainfall events here in Bermuda. And that got brought into the synthesis papers reports as well. And then, of course, sea level rise. I talked about the fact that the sea level is rising. This is roughly the order of magnitude we can expect. So when my grandfather got off the boat from St. Kitts 100 years ago, the sea level was about 2 Coke cans shorter than it is today. In about 20 years, it'll be another 2 Coke cans taller. So it means that the rate of sea level rise is accelerating over time. And we're seeing some instances where when we get an extreme oceanographic event that may or may not be related to climate change, we get a preview of what the future might hold. This is at Somerset Bridge in 2019, I think that was. And there were some high profile events as well where the square in St. George's flooded and people were sailing boats down the square, sunfish. So some of these impacts are that hurricane wind risk this century is already up by over 5%. Lots of uncertainty around that. We'll get into how we know that in a bit. This rainfall flooding event frequency in today's climate, or maybe it was last decade's climate, it's about, on average, once every 2 months. And there's about $3 million more worth of annual rental value exposed to coastal flooding events in the next 50 years or so. We're going to get into some of this as well, if we have time, which I think we do. So we took some of this information and tried to build what insurers use. They have these tools which are often considered black boxes. They're opaque. You don't know what's in them. That are called catastrophe models. They have a lot of detail about hazards, exposures, and vulnerabilities, and their purpose is to reveal what the cost of a damaging event might be and aggregate the amount of risk over time so that an underwriter can say, this is how much the potential for damage will be, so that's how much premium I will charge. How do they get that? Well, we built this open source risk model based on freely available data. We have a lot of data sets available to us from the U.S. National Hurricane Center and NOAA, and also from the Bermuda Weather Service on hurricanes, how intense they are, how big they are, how close to the island they get, how fast does the wind speed blow when they get here, how low is the pressure. All of these are the physical aspects of hurricanes that I, a meteorologist, would be very interested in. But it turns out, and I learned this during my short stint at a reinsurer, that in of itself is not enough to really price risk. You also need to know about the stuff, the property, the people in harm's way. We call that exposure. And exposure can be characterized by, if you're looking at property, how many buildings are we talking about that's in the path of a hurricane? What are the ages of these buildings? What are they built out of? What are their occupancy? Are they churches? Are they houses? Are they apartment buildings or hospitals? This construction type, did it adhere to the building code? How old is it? So all of these are bits of information that go into the exposure component of these risk models. Turns out we've got a pretty good exposure data set that the government publishes. It's called the annual rental value data set that they put out there every year, I believe it is. And I think there's a survey out now to try to assess what the rental value is of each property. And there's some secret sauce that they put in there to try to assess tax, but we don't care about that. We just want to know, is there a property that we can identify and how much is its value? And then we can sort of make some building on our own fudge factor about, well, if we say the average property, the average house in Bermuda is on average $1 million. Add some kind of factor to adjust the data set, and we've got a property data set for Bermuda. But what about vulnerability? Well, all this is saying, what does X wind speed, how much damage does X wind speed cost or cause? And it turns out there was a very interesting damage survey done during Hurricane Fabian in 2003, probably our most devastating weather event in the last century. Well, in the last 70 years, I'd say. But what they did was they went out and looked at the proportion of white roofs after the storm, which were covered by blue tarps. Because back then, you couldn't get a tarp other than a blue one. And so you had this really nice high contrast view using aerial photography where you could actually pinpoint what properties had been damaged and come up with a proportion of damage that had been caused during the course of the storm, and then map that to a wind model of where the winds were highest around the island. And from that, you get this function of wind speed on one axis and proportion of damage on another. Now, granted, this was just one storm. And so you run your synthetic storm over your property data set, and you calculate the potential for damage, and you assess a cost, and then you repeat that lots and lots and lots of times, and there's huge uncertainties in doing all of that. So that's what we did. We built a risk model based on the available data that's out there, and we published it. And here are some of the results. To start off with, here's the long-term record of hurricanes in Bermuda. This is the frequency of storms from the 1800s through till it was about, I think we did this in 2018. So the long-term record. And to be sure, you can see lots of bumps and wiggles in the signal, but there's an inexorable rise in the background trend. And what we did was we looked at, well, what is the background risk for the whole series? And then what's the risk during these low periods? And what's the risk during this most recent high period, the last 20 years or so in the record? And we found that, there was an increase in risk of something like, for looking at the long-term record compared to the short-term record, there's something like an increase of 5 to 7% of risk. Now, keep in mind a couple of caveats here. The total property exposure value that we estimated in our dummy portfolio of property data was somewhere on the order of $75 billion in Bermuda. And so this is looking at the proportion of that would be damaged by an event that's like, that has a probability of 0.2%. And, it gives you some insights about, yes, the risk is increasing, but the really eye-opening thing was that the variability around that, and this is just plotting the standard deviation, was vast. So it meant that not only is the risk incrementally increasing, the cost of damage being, the potential cost of damage of hurricanes is increasing. The big swings between the top end and the low end are getting bigger as well. And this is a common theme we see when we think about climate change. The background is going up, but then the variability, the extremes are getting bigger as well. So as one might expect, the high frequency periods, this likelihood of damaging wind speed increases, and so the risk to property is increasing as we go. And uncertainty increases due to the hazard record deficiencies as well. So it means that, what do I mean by that? When we go back to the early part of the 1900s, before World War II, we didn't have weather balloons, we didn't have satellite, we didn't have radar when it's working, we didn't have we didn't have flight reconnaissance. So it meant that there's a lot more uncertainty the further back in time you go. But nowadays, we've got pretty good ways of measuring things. So our summary when it comes to this type of work is that we have lots of large changes in the the potential for damage versus wind speed, and we generated this kind of framework for doing a plug-and-play risk model. And some of the work that I hope to do going forward is to actually build on that. The final part of my talk here, which is going to be very short, is looking at that relationship between ocean temperature and hurricane intensity. So this was a wide-ranging collaboration with groups from Ireland. One of my former interns at BIOS, Samantha Hallam, did this work in 2019. She was actually here for Hurricane Umberto. And we published a paper in 2021. She finished her doctorate and is now at the Irish Climate Analysis and Research Unit, or ICARUS, because we love acronyms. So through some work funded through Ireland, in collaboration with the University of the West Indies in Jamaica, and of course us here at BIOS, we've started rolling out this approach, which I'm going to tell you about, to the wider Caribbean. So our motivation is that we look at the record of hurricane activity here in Bermuda, and we see that there's been an increase in the maximum sustained winds of about 30 knots over the past 60 years. And that's pretty well correlated with the summertime temperatures of the upper ocean near Bermuda. They're increasing on the order of 0.17, 0.2 degrees Celsius per decade. So it means that hurricanes are getting stronger. We think that's because the oceans are getting warmer, or the ocean near Bermuda is getting warmer. And again, this is published work that we did. Take that approach and expand it across the Caribbean region, Caribbean Sea, and we're finding very similar findings that, the wind speeds of tropical cyclones or hurricanes are increasing by about 30 knots since 1965. And again, tightly correlated with these upper ocean temperatures increasing, the warming of the upper oceans. Again, rising at about 0.2 degrees Celsius per decade. So we adapted a very old model, a 40-year-old model from Kerry Emanuel, that uses thermodynamic theory to predict what the potential intensity a storm could get to is based on sea surface temperature. But we adapted that to use real measured data instead of models. We looked at real data coming from ships, such as the Atlantic Explorer. We looked at real upper ocean data also from autonomous underwater vehicles and Argo floats. I'm sorry I wasn't able to bring one here tonight, but you got the water bottle instead. And upper air soundings from weather balloons. And that's my current student intern, Max Santiago, who's Bermudian. He's studying atmospheric science at Purdue University. So it takes input, this model that we built and adapted from Kerry Emanuel's original code, takes in all these inputs from real data and not just model inputs. And just a side note on some of these inputs. This plot shows all the locations going back through, I guess it's several years, of Argo floats. Now these are devices that, let's use this, that have a valve in it that increases and decreases the buoyancy of the device. And so it's sort of squirting water in and out of the top, or maybe the side, I'm not sure where. And as you increase the buoyancy, it floats up. You decrease the buoyancy, it goes down in the water. And that's all it's doing. It's going up and down in the water and drifting with the currents, measuring temperature and other constituents of the water as it goes, and relaying that information back to the scientists via satellite. Now, if I take that Argo float and it's going up and down like that, and I add wings and a tail and a rudder, it starts doing this. And that is a glider, an autonomous underwater vehicle that we can pilot. And it has very little demands on energy because it's just a piston. It doesn't have a propeller. It's very, very slow, but it does stay out in the water for months at a time. And so we can fill these periodic data gaps with things like gliders And also, an added advantage is you don't have to pilot a ship into a hurricane. You can pilot an autonomous drone under a hurricane, measure the ocean temperature before, during, and after a storm, and get that data back relatively cheaply. So we've been sort of expanding the fleet of these gliders and have more plans to do so. Sending a ship out and taking these very granular observations using instruments like this on a big rosette, it costs something on the order of $25,000 to $30,000 a day to run. These instruments, very low cost to run over time. They might be expensive initially, maybe as much as $250,000, but then once you've got them, you can run them very cheaply. So anyway, these are some of the data capture platforms that we use to get data that gets input into the model that we've been developing. The output from this model is maximum sustained winds and minimum central pressure. And you can see a plot here from Hurricanes Gonzalo and Fabian, Gonzalo in 2014 in red, and Fabian in 2003 in blue. And you can see they were very similar in terms of intensity, but actually they had very different impacts, didn't they? There's various reasons for that, one of which is that Gonzalo came at low tide. So our results, if you look back in the Bermuda Atlantic time series of temperature data, each of these is a depth, each of these different colored lines is a time series of the temperature at a given depth. So the surface is that blue line, the red is 25 meters, the green is 50 meters, et cetera, et cetera, et cetera. And you can see all the way down to 300 meters, the ocean is gradually warming up over time. And here are your years on the x-axis here. Now, in our original model that Carrie Emanuel built, he used sea surface temperature. And what you're looking at in the far right is using that model for the hurricanes that we've had here in Bermuda to predict what the potential maximum intensity in terms of sea level pressure would be. And on the y-axis, which I will highlight here, is which I'll highlight here rather. This is the model output, and this is the actual, what this storm actually had. You want those dots there to be as close as possible to the line. If they're certainly perfectly along the line, then it means the model is perfect and is making a perfect prediction. No models are perfect. We'll get into that. At least in our model, we were able to improve upon that by using upper ocean temperature and not just sea surface, because the sea surface is what the hurricane feels, but the real source of energy is below the surface that feeds into the storm. So we were able to use this model to relatively accurately predict the potential intensity of some of the hurricanes that move past Bermuda. And the highlight of this slide is really this, for me as a forecaster, because we were playing with this when I was a forecaster again, was being able to say this to a decision maker. Environmental conditions near Bermuda would support a Category 4 storm based on observations theory and historical data. That's all I care about. I don't need the peer-reviewed publications. I don't need anything else. I just want to be able to say something that is of use to a decision maker so that they can actually act on it. And we've sort of run this through the Caribbean as well. Just to give you a sense, this is from Hurricane Beryl in 2024, when the Caribbean Sea was about 1.5 degrees warmer than average at the time. And we had some pretty good success with Beryl as well before it made landfall near Jamaica, before it impacted Jamaica and messed up my plans to go to a conference there. And we've done that with Hurricane Ernesto in the same year, 2024. So that we can use it in this kind of like real-time forecasting mode of saying, okay, we're forecasters or we're emergency planners, we're disaster managers. We want to know what this storm is going to do, excuse me, or how intense this storm is going to be when it gets here. Now you can also look at using this type of approach in a counterfactual view. What that means is you can take a look at an actual storm with real data, and then you can hold everything else constant and move the ocean temperature to see how much stronger or weaker it would have been in the model world, at least, given that change. Hurricane Sam in 2021 was the strongest storm to come within 200 miles of Bermuda. It was nearly a Category 5, and that was in 2021. The triangle there is showing you the actual estimate of what Sam's intensity was in wind speed and knots. The model estimation had it slightly higher. That's okay. What we did was we took all the same parameters that we used to model Sam, that weather balloon launch, the upper ocean temperature from ship and glider data, the weather observations from the Bermuda Weather Service, and we modeled it as it actually was. And then the only thing we did is we changed the ocean temperature. And by changing the ocean temperature, you get a sense of how Sam in 2016 might have been, or in 1992, or in 1980. So Hurricane Sam in 2021, a nearly Category 5 storm near Bermuda, if the model is accurate, the ocean temperatures would only have supported a Category 1 storm back in 1980. So it shows you the ongoing effect of warming of the ocean. So you can use that in the opposite direction, future projections. And this is some work that we're just finishing up. It's in review now for publication, that basically says that for every 1 degree Celsius rise in temperature in the Caribbean Sea, of the ocean temperature that is, for the top 100 meters, you get a 27 knot or 31 mile per hour increase in storm strength on average. Some storms strengthen more than others, but this is on average. There's more detail coming out in the paper. So we can also use this for like future projections. Here is Hurricane Nicole that hit us in 2016 as a Cat 3 storm, 100 plus knots of wind speed. By now, nearly, 10 years later, the projected intensity, potential intensity for the model says that it would have exceeded Cat 4. By 2050, that particular storm, all else being equal, would have been a Cat 5 in the model world. So, got 25 years before this could become a reality. And then we repeated that experiment with all the storms in a 30-year period. Now, the big downside of this analysis is that, well, one of the big failures of this analysis is that when Fabian came through, there was no sea surface temperature data. The ship had not gone out within a few months of the storm's approach, but that's okay. We have plenty of other storms to play with. What we found is that, using that model representation of potential intensity, we're seeing this increase on average. The green crosses here are the average of all of those 30 years worth of storms. And, going forward, 2050, you can see the averages going from what today's might be a Category 2 storm. Your average storm that hits Bermuda or comes within range is a Category 2 on average. You can see there's a big range, there's a big variation. By 2050, that might have increased to a Category 4. But again, remember what I said, big variations. That uncertainty goes crazy the further out in time you go. And then so far and so on, you have by 2075, you might expect your average storm moving near Bermuda to be a Category 5, if our model is correct. So here's your upward trajectory. The modeling indicates that projected upper ocean warming will lead to stronger Bermuda hurricanes. How much stronger depends on the storm. There's a lot of uncertainties here. We haven't accounted for a number of things. And also, keep in mind this axiom from a famous statistician in the 70s: all models are wrong, but some are useful, meaning that all models are simplifications of reality and therefore technically inaccurate. Here's a model of Earth. Oops, we'll have a model of Earth. Here's a model of Earth. Is it perfect? No, I don't think I can even see Bermuda on this. But it's useful. We can see an approximation of the globe. It's not a perfect sphere like this. It doesn't have a nice line drawn through the equator, but it's useful for us to get some idea about distances, directions, latitude, longitude, and locations of continents and oceans. But it's a model. It's necessarily wrong. And just like that, our model is wrong, but it may be useful. What it's predicting, for example, is that the actual reported average, the average of all of the actual storms during that 30-year period was 97 miles per hour. The model says it's 103. So there's already, from the starting point, a bit of a difference. But models like we use for predicting hurricanes are essential for understanding complex systems. You can't possibly begin to think about understanding the Earth without first looking at a globe. Making predictions, like we do with hurricane forecast tracks, those spaghetti tracks that you look at every season, which are incidentally getting better and better as time goes on, and also guiding decision-making. But I think this last part of the statement is so important, provided their limitations are understood. So it takes not just looking at a computer output, it takes someone with experience and expertise to interpret that output to really get a useful piece of information out of it. So some caveats there, much more work needed on this, lots of large assumptions. The upper ocean temperature change was the only thing we changed. We didn't account for any changes in atmospheric parameters. We did not account for any future changes in salinity of the water column or density. Nonetheless, it still seems to be a useful tool, and you can go and run it yourself if you like, because it can run on a desktop, it can run on a phone. It is a very simple model that we've developed, and it's, again, an open source thing. That's how some of us like to operate, is to provide tools that are actually useful and not just purely esoteric and academic. I'll let you get that. I can come back to that later if you want. So what's next for us and me? We're going to develop at BIOS more of this autonomous ocean monitoring capacity. We're in the process of, we've hired a faculty member who's going to take over the glider facility, the glider lab and function, and all the marine autonomous technology. We're actually going to be building a facility if we can get around to submitting planning permission. We're going to be doing some more modeling of these regional hurricane intensities, and we're working with folks in the Caribbean on that. There's still some effort to continue the climate task force. We've taken a bit of a pause and a hiatus, but I think that's coming back to the fore fairly soon. And then one of the things I haven't talked very much about is the fact that BIOS is now affiliated with Arizona State University out in Tempe, Arizona. And they have a presence, they've been, to summarize it, building their enterprise around sustainability, around understanding the planet and providing solutions, and you can't do that in isolation in the middle of the desert. So they've acquired BIOS, and they've also acquired and are working with groups in Hawaii. And so because some of those groups in Hawaii are working with islands, and I know a few things about islands, we're working together to try to build a network of island resilience, focusing on science, policy, risk analysis, some of the types of tools I've talked about here tonight, with a view to bringing them to the communities that we serve, not just sort of sitting in a back room and doing computer code, but actually going out and figuring out how those communities can benefit from these tools. So that's pretty much it from me. I'll just go to the link here of the Bermuda Institute of Ocean Sciences. This is our website, bios.asu.edu. There's a lot more information there. The things I've talked about tonight are really focused around my work, but there's a lot more work that's been done at BIOS that it's centered on some of the other aspects, the biogeochemistry of the ocean, the coral reefs, and the deep water oceanography as well. So with that, I'm going to say thank you very much and finish up. Sure. We've got questions? Easy ones only, please. Dr. Sam. Argo floats? No, they're out there for months at a time, I believe. They will, well, they're drifting with the currents, so you can actually deploy them and leave them, but then if they stop functioning, you can go out and get them. So they have GPS as part of their package of data that they transmit back to the users. No.
Okay, second question.
Yes.
The climate, the second part.
The reports, yes.
Focus on, thank you.
Society impacts and societal risk.
Right. My question is, what are some of the outcomes in terms of Bermudians and their willingness to change their behavior to help mitigate the impacts of climate change? Did that come up a little bit?
So the report really focused on the impacts and was geared towards focusing on adaptation as opposed to mitigating the effects. There was a small piece in it that I put at the end of that particular report that focused on the fact that each of us on average per capita emit something like 10 tons of carbon dioxide every year by virtue of the activities that we undertake. Some of that is well beyond our control. Much of that is because we are a small island and we ship everything in using ships that use fuel, including fuel to burn, to generate electricity. So there are aspects of that that sort of are kind of teased out in the report, but the focus of it was really like, these are the risks coming down the pipeline. To change? I think so. I mean, as evidenced by, for example, you all being here tonight, the fact that we had a packed lecture hall yesterday for the students. I think there are changes coming. I think there is a growing recognition globally, no matter the sort of bumps in the road that happen politically, that, you know, these are real risks. These are really happening. Every time you turn on the news, wherever you are in the world, there's a drought or a flood or a tornado outbreak or a hailstorm or a wildfire, which is becoming even more devastating in parts of North America. So I think the writing is on the wall. People have woken up to this notion that, you know, the climate is changing, has changed, and will continue to change. And, you know, if we don't do anything about it, then we continue to be in trouble. Question. Yes.
One of the things I was wondering about was how hurricanes impact those environments, because you know we have endemic shrimp and all that stuff, and as well as people visiting, and that's part of it too. Because anyone wanting to know what the societal impacts are for some of this, it's a strong thing for our mental health to visit these natural places. So if you continuously have hurricanes, we don't hear a lot about how it's impacting those environments and the capes.
So one of the, this is really useful. I think the stuff that I've studied is a very small piece. And I think, you know, you're all scientists, so you all know we all studied a narrow piece of the puzzle, and there's this much wider interdisciplinary impact. I'll focus on groundwater because that's one I do know a little bit about. One of the students that I had, Caroline Alexander, in 2022, who actually contributed to that report, her master's thesis was on sea level surges and impacts on salinity in the groundwater. So it means that one of the things she found was that at the borehole in, I think it was in St. George's, after one of these big sea level events, about 6 hours, measured at the tide gauge, about 6 hours later, there was a lag effect. You see the salinity and the water quality, the salinity spike and the water quality decrease in that borehole. And so it shows that, yeah, there are impacts going on that we don't see, and especially in environments that we're not always in. We all see the vegetation getting blown around and being left on the railway trail and things like that, but I think there are these effects behind the scenes that bear a lot more study.
Because it was also the situation where you had, when in the summer you used to get these very still long periods where it's very hot in the ocean, and then you get a storm blows through, and all of a sudden you started having fish die
Yeah.
because of the thermal.
Yeah.
So, I mean, that was something we didn't anticipate. But people are starting to look at it. Unfortunately, well, fortunately, in one sense, it doesn't happen very often. But when it does happen, it's, you want to know why.
So it's interesting you say that. There's a series of studies that one of our other Bermudian scientists at BIOS, Rachel Parsons, is doing, looking at how the oxygen in Devil's Hole changes exactly with the process that you talked about. You get this long period of calm conditions, stratification of the water column, eutrophication even, that reduces the amount of oxygen. Then a storm comes through, overturns that, and you get a lot of nutrients stirring up, and you get a plankton bloom in the water. You have a question? Uh-oh.
Whilst we have the oxygen in the water, there's something that you said initially that I kind of just want some clarification. So you said the ocean temperature is rising and there's less oxygen in the ocean, right? And there's slightly more carbon dioxide in the air, and therefore it's causing acidification of the ocean.
Yes.
Because it's dissolving more. So my question is, with respect to the ocean, what makes ocean water do so? Because generally, the oxygen part makes sense to me, where gases are less soluble in heated anything, in liquids. But what makes carbon dioxide in the ocean dissolve more versus, for example, a Coke that you have, if you put it out, it gets hot, the carbon dioxide wants to escape. What makes carbon dioxide dissolve more in ocean water versus oxygen?
I think the partial pressure of carbon dioxide in the air is increasing, and so it's actually forcing more carbon dioxide. So it's not that you're not getting outgassing. It's that the balance of that is disturbed. So you're actually getting more carbon dioxide than normal going into the ocean. So it's not like you're getting sort of like heavily acidic water, but it's getting the pH is decreasing. I was really testing my chemistry here. Does it make sense? Just remember, I'm a meteorologist. He tell you what the clouds are. Right? I mean, it's worth a conversation. We have a lot of really good biogeochemists at BIOS. In fact, one might argue that that's been one of our biggest contributions to the IPCC, the Intergovernmental Panel on Climate Change, is focusing on this ocean acidification piece. And it could be, I've heard it referred to as ocean acidification, but I've also heard it referred to as, what's the word? It's dealkalinization. So it's still alkaline, but it's becoming less so. Yeah, I hope that's helpful. Okay, good. That was one question? Okay, right, all right.
Are you doing any work? You said you're doing work in Durban. Are you doing any work to get out from there with Dominica? Because we hit a lot by hurricanes. I know there's a big ethos back to be climate resilient.
Yeah.
So is it part of the study that you do?
So short answer is yes. I mean, sorry. So the question is, are we doing any work with Dominica in the Caribbean? Because they are particularly exposed to, or have been exposed to, some very intense hurricanes. I think Hurricane Maria in 2017.
From San Francisco to okay, fine. I'm turning off the electricity now to pause.
Mhm.
Hear from them, no word.
Yeah.
From
Yeah. So,
after the hurricane.
so I mean, Dominica is one of many countries in the Eastern Caribbean that we are not specifically working with, but we have been doing some work with the Caribbean Institute of Meteorology and Hydrology, which is based in Barbados. And they are part of this Eastern Caribbean consortium as well. So hopefully Dominica will benefit from some of this work as well. But just in the same way that I showed, in fact, I'll go back to it, just in the same way that I showed this, this tool that anyone can use, we have like rolled this out amongst all of the meteorological services in the Caribbean. So they have access to it already. And now we're just trying to continually refine it. And once we get it published, we can then start to share the code and make sure it's the best it possibly can be. So that was question 2, right? Okay. Thank you. Amy.
Well, maybe other ones have to say, but I'm fascinated by your relationship with Ireland. And she's a
Former intern.
Yeah, so can you speak about some of the impacts that they're seeing?
Oh, right. Okay. So one of the things that Sam is doing is, so she's got this work, but then she's also doing stuff on how cyclones are moving, how cyclones that were formerly tropical cyclones, like hurricanes, are starting to impact Ireland, Northwest Europe, are actually, you know, they're retaining more of their tropical characteristics as they go into the European, into those latitudes. Yeah, I mean, that's not just that's not a recent thing either. I remember in 2005, there were some storms which impacted Spain, and we had a contingent, my PhD advisor, a colleague from the Hurricane Center, another colleague from Florida State, and me, my newly minted PhD in hand, went to Madrid to train all the Spanish Met Service people on tropical cyclones, because they're not used to forecasting them. So there's this interesting interaction between the Met services around the world and researchers around the world. It's a surprisingly small community. Any other questions? I'm looking at you, Dr. Sam.
Well, my questions were all answered.
Good. Thank you, sir. Yes. Thank you.
You have different devices that are in the ocean. I have taken my great nephews there when they were younger at Bias, and I think it's a great opportunity.
Ma'am. Sorry. So.
Okay, I said that your presentation was very informative and insightful, and I certainly have been to Bias when you used to have open house. I'm not sure if you still have that anymore. But what I want to know is all these different devices that you put into the ocean, does that have any impact on ocean-going vessels? Like, or do they know where they are, or, you know?
Great question. So the instruments such as, let's see if I've got such as these gliders, as you can see, they're very brightly colored. They are emblazoned with sort of, this is a scientific piece of equipment. They have GPS, and so every time they pop back up to the surface, they send a burst about like where they are. The ocean's actually got a lot of space between vessels, and so it would be very unlucky to hit one of these. I think these are quite resilient. They have been, we've retrieved them. They've been bitten by sharks and shaken around. We figure they've run into whales and like run into potentially vessels from time to time, but we never get reports of, oh, we lost one because it hit something, or conversely, getting irate people calling up saying, your glider that looks like a torpedo hit my boat. We don't get any of that. So I think it's a big enough ocean that they are avoided. Thank you. Oh, I see two more questions. Yes.
We're talking about those smaller little things that bob around in the ocean.
The Argo floats?
Yeah, small, that they have GPS so you can track where they are. Approximately how far do they travel in their routine?
Good question. They go with the currents. Let's see if I can find a picture of one, just so that, sorry, avert your eyes. No, bear with me a second, just so you get a sense of scale. Yeah, there's one. So that's how big they are. They're not tiny. That's a deployment of one of them. And they can travel for months, and it really does depend on the currents. As some people in the audience will attest, if you launch a vehicle like this into the ocean with no propulsion, it can end up, well, in some cases, you hope it ends up in Ireland. In other cases, it might end up back in Bermuda. So yeah, it really does depend on the currents. Julio.
With climate change affecting intensity as well as the frequency of substitute events, can we see like a chain reaction of phenomena such as hurricanes in other parts of the world that affects rather than
So I'll reinterpret your question. Can you see hurricanes in different parts of the world that you wouldn't normally see them? And is that a fair interpretation? Okay. So yes, in fact, and I'll show you this map again, just to give you a map. Usually, like I said yesterday in the masterclass to the students, hurricanes and tropical cyclones, and in the Western Pacific, they're called typhoons. They occur because of warm water in the tropical oceans. That's where they form, that's where they spawn and intensify, and then they move out of those belts into the subtropics, like where we are, and into the mid-latitudes. Given some circumstances, you can get these events happening in, say, the Mediterranean. So up here, you can and we have seen instances where that storm, like Hurricane Karen I talked about, that subtropical storm, those types of events can happen in the Mediterranean, and they're called medicanes. One's even been found to have formed in Lake Huron, in the Great Lakes. So given the right conditions, these types of things can happen elsewhere. And as the oceans warm, and if the conditions are right, you can see these types of things popping up in different parts of the world where you don't normally see them. Part of the reason you don't see many tropical cyclones in the South Atlantic is because of the wind shear, the fast-moving, windy environment. It's a bit counterintuitive, but with changes in wind speed with height, if you have a hurricane moving into that environment, it can actually be tilted over and sort of kill its own circulation off. Usually, the winds in the South Atlantic are too fast to support hurricane activity, but every once in a while, you do get these subtropical type storms forming. They seem to be becoming more prevalent, and they're impacting places like Brazil, where they might not be used to these types of impacts. You heard me talk about tropical storms and hurricanes impacting Spain. Well, more tropical storms than hurricanes, but yeah, so to answer your question, yes. I mean, as the world, as the ocean and the atmosphere changes, you're going to see things that are quite unexpected in different places. And on that cheery note, I'll say thank you very much for your attention this evening.
So on behalf of the college, we would like to thank you, Dr. Gashard, for allowing us to have so much interaction with you for this week. I know it has been a lot. You've dealt with us quite a bit, from the radio station interviews to the masterclass and even to the night. So we would really appreciate you coming and giving us information on things which are very pertinent to us here and now. I'm currently in Bermuda and in the wider Caribbean. And we'd really like to just give him another round of applause, please, and thank him very much. We'd also like to once again thank our corporate sponsors, ROCHE, SANS. Every year they hold this event, and we appreciate our corporate sponsors. Can we have another round of applause for them, please? And lastly, we could not have this evening without the people who are in attendance. Thank you all so very much. We appreciate you. We are part of you. And without you, we would not exist. And therefore, give yourselves a round of applause for being here with us this evening. Thank you all very much. And we hope to see you next year at our ROCHE Science Week.